Hello guys, and thank you for watching this video lecture. This lecture is about formal query language. Before we begin, let's outline the agenda for today. We will cover three main topics: relational algebra. This is the procedural language for querying relations. The second one is Tuple Relational Calculus. It's a non-procedural way to express queries. And the third one is Domain Relational Calculus. It is kind of another non-procedural approach with a focus on domain variables. These concepts form the backbone of formal query language in databases, and understanding them is crucial for working with relational models. Relational algebra is a procedural language, meaning it specifies how to retrieve data step by step. It takes one or two relations as input and a new relation as output, right? Then we have some operator here. We have select as shown by sigma for filtering rows. Then we have project to select columns. Then we have union, intersection, and set difference for combining relations. We have rename for altering attribute names. These operators allows us to construct complex queries from simpler ones. And this is our schema diagram for a university database, and all the examples will be based on these database. So we have a student table with these attributes, advisor with these attributes, department with these attributes, and this underscore, it means primary key. So we have instructor tables with ID, name, department name, and salary. Then we have course table, prerequisite table, takes, time slot, teach, classroom, and section tables. So the first operator is selection operator, we show by sigma PR. This selection operator filters tuples from a relation based on a condition, right? So then we can say sigma PR is T tuples in such a way that T are in R and the condition is satisfied, right? We can use and or not in here. Also, we can go for some operators like equal, not equal, greater than, or equal, less than, or less than, or equal. For example, I want to find all instructors in Department of Physics. As you know, in the instructor, we have instructor ID, instructor name, department name, and salary. So I want to find out all information of instructors if their department name is physics. So I should go for table as instructor. Then in here, I should go for selection, and where the condition is department name is equal to physics, right? So selection of department name, all tuples from instructor table if the department name is equal to physics. Then we have project operation. So here we can have some columns or attributes A1, A2 up to AK from the relation of R. So these are our attributes name, and this is our table name. The output will be a relation with K columns with the number of attributes that we are interested in. For example, in instructor, we have how many columns? We have 4 attributes: one, ID, name, department name, and salary. I want to have a table here, but I don't want to have column of department name. It means I want to have a table with ID, name, and salary, right? So what I do here, projection of ID and name and salary from table of instructor. Then we have union R cup S. In here, it will give us all the tuples in such a way that tuple are both in R or in S, right? So it's a union. If I want to go for set notation Venn diagram, if this is R and this is S, it means all, everything, right? Everything here. The T, the tuples, either in R or in S. And in here, there is some condition. R and S must be array. It means they have the same number of attributes. And also, the attribute domains must be computable. So, for example, I want to find out all courses taught in fall 2009 or, this is or, spring 2010 or both, right? So from here, we understand that it is union, right? Then we go for courses. So courses are in which table? In section table. So section, from section. Then it says all courses. For example, we want to get course ID only. Course ID. So we say projection of course ID from where selection, we have a selection, semester should be equal to fall, year should be equal to 2009. So we say semester is equal to fall and then year is equal to 2009. Then it say or, so this is or, the same thing here. So we say pi course ID, then again selection of semester, this time is equal to spring, and year is equal to 2010 from where? From section. In this way, we can write this query. Next, we have set difference. Set difference, it means all the tuples are in R but not in S, right? So whatever is in R but not in S, right? Or you can say R minus R intersection S, right? So using Venn diagram, I can say it is R, this is S. So whatever is in R but not in S, it means this part is not included. So for example, find all courses in 2009 but not in spring 2010. The same thing, right? Pi. So this time we go minus. The other things is the same. Pi course ID, then selection of semester is equal to fall, and year is equal to 2009 from section, then minus the same. Pi is equal to course ID, then selection of semester is equal to spring, and year is equal to 2010 from section, right? The only difference is minus, but not in 2000, spring 2010. Next one is intersection, or you can say R cap S. This one is similar to OR operator, and this one is similar to AND operator. This one returns all the tuples that is in both R and S, right? So in Venn diagram, I can show like this. If this is R, this is S. We are interested in this part. Again, they should have the same array and they should have computable in terms of domains. So we can write R cap S as R minus S. So R minus S is this part. So we are interested in the same, right? This one is the same as R cap S. Then we have Cartesian products. Cartesian product pairs every tuple from one relation with every tuple from another one, right? So we can write this one, we will repeat. So we can say TQ, T in R and Q in S. We will repeat all the tuples of the second relation for every tuple of the first relation. And we have some conditions here. Attributes of R and S are disjoint. Then R and S is equal to 5. It means they are disjoint. It means like this, right? It is R, for example, and S. They have nothing common. So if attributes of R and S are not disjoint, then we go for renaming them, right? So what is rename? This is to rename and therefore to refer to the result of a relational algebra expression. So this allows us to refer to a relation by more than one name. So we will rename it. So output will be the expression E under the name of X, a new name. For example, if a relational algebra expression E has n already, right, then the result of expression E under the name of X and with the attributes of A1 to A. So we can rename E as new name like X. For the relational algebra, we have union, set difference, Cartesian product, selection, projection, and rename. Then the next one is Tuple Relational Calculus. Unlike relational algebra, Tuple Relational Calculus is non-procedural. It means queries specify what to retrieve, not how. And each query is in form of this one, T given pt, right? It is the set of all tuples T such that predicate P is true for this T. So T is a tuple variable. T is a tuple variable, and TA denotes the value of tuple T on attribute A. So T is in R denotes that tuple T is in relation of R, and P is a formula similar to that of the predicate calculus. We have attributes and constants. Then we have comparison like less than or equal, not equal, greater than or equal. We have set of connectives like and or and not. Then we have implication. When we write x implies y, it means if x is true, then y is also true. So if x is true, y is also true. You can write like not x or y. Then we have set of quantifiers. So we call this one as there exists. So this one, it means there exists a tuple in relation R. There exists a tuple T in relation R such that predicate Qt is true. And this one is for all. So this one is there exists, and this one is for all. So for all, it means we say Q is true for all tuples T in relation R. For example, here I want to find out ID, name, department name, and salary for our instructor whose salary is greater than 80,000, right? So I write in this way T in such a way that T is in instructor table, and T salary is greater than 80,000, right? So I write tuples. Please give me the tuples in such a way that T is in instructor, belongs to instructor table, and T salary, it means the salary attributes in T is greater than 80,000. Or we can write in this way, ID attribute, we can write T, there exists is in instructor TID is equal to SID, TID is equal to SID, and S salary is greater than 80,000, right? So this T, the result is the set of tuples T that satisfy some condition. So this T represents an output tuple. In this case, it means one instructor record from instructor table. Then we write there exists S in instructor. There exists a tuple S in instructor table. The query search for at least one instructor S who meets these criteria. Then we say TID is equal to SID. This ensures that the output tuple T refers to the same instructor as S by checking the same ID. Then we say salary greater than 80,000. This the condition that instructor's salary must be greater than $80,000. Next, find the name of all instructors whose department is in Watson building. So we write T, right? T, there exists S in instructor where T name is equal to S name, T name is equal to S name, and there exists U in department where U department name is equal to S department name and also U building is equal to Watson. So again, this T is the result of tuples, and T represents an output tuples containing the name of qualifying instructors. Then in here we say there exists S in instructor. It means the query search for instructor S who meets these criteria. Then we have T name is equal to S name. This ensures the output tuple T contains the name of instructors S. Then we say there exists U in department. There exists a tuple U in the department relation, and this checks the department table for additional condition that we have here. What is the condition? U department name should be equal to S department name. This links the instructor S to their department U by matching the department name. Then we say U building is equal to Watson. This is the critical condition. It means the department must be located in the Watson building. Find the set of all courses taught in 2009 or spring 2010 or both of them. The same thing that we did in relational algebra. So this time we write T, there exists S in section, where T course ID is equal to S course ID, right? And S semester is equal to fall, and S year is equal to 2009. Then there exists U in section, the same T course ID in U course ID, right? Then and U semester is equal to spring, and U year is equal to 2010. In this way, we can do it the same thing but different notation. Find the courses taught in 2009 and in the spring 2010. In this case, just we need to change this or to this one, right? Or to and. So in here it says or, but this time it says and, right? The only thing is to change this one. So this time it says find the set of all courses taught in 2009 semester but not in spring 2010 semester, right? Two ways, you can use minus or you can use not. Find all students who have taken courses in biology department. Okay, we write in this way. T, there exist are in a student table. T ID is equal to RID. And for all U in between all courses, right? For all course, all in course, U department name is equal to biology. Biology implies there exists S intakes where TID is equal to SID and S course ID is equal to U course ID. I explain what happens here. So first, this has three parts: student identification, universal quantification, and also enrollment verification. So in here, we say there exists R in a student where ID is equal to RID. So this ensures the output ID corresponds to valid student ID in the student table. And this part is technically redundant if TID is already bounded to a student, but it clarifies the domain. Then we have a universal quantification of for all, right? So this for all courses U in the course table, this query checks a condition for every biology course, right? Then we have this implication. This says if this U department is equal to biology, then what happens here, right? So the condition after this implication must hold for every biology course that we have here. And then we say there exists S intakes where student ID is equal to SID and course ID is equal to U course ID, right? This ensures that a student TID has taken the biology courses U, like for example, there is matching record in the takes table. There exists an enrollment record S where the student took the course U. It is possible to write tuple calculus expression that generate infinite relations. For example, you write T in such a way that T is not in instructor. This is not, right? So it means this query select all tuples T that do not exist in instructor relation. The issue here is since there are infinity many possible tuples with arbitrary values for ID, name, department, salary, etc., there are not in the instructor table. This query would return an infinite relation. So this will be there are infinity many tuples that are not in instructors. So why this problem happens? Relational databases assume finite relations, tables with finite number of rows. But when we say not T in instructors, this violates this assumption, making them unsafe, or you can say impossible to compute in infinite time. To prevent infinite results, we restrict the domain. We restrict the domain of variables to active domain values, like values that actually appear in the database or query. So we restrict the set of allowable expression to safe expression by domain of tuple relation formula like P. We can say domain T instructors and T salary is greater than 80,000. This is called as domain restricted. Only consider tuples T that exist in instructors. And the result will be instructor greater than 80,000. So we define that safe expression in Tuple Relational Calculus that used to ensure the query result is finite and computable. So we can say for a query of the form of like T and such a way that PT, where this PT is a logical condition. This is every component of the output tuple T must be derived from existing relation in database and constant explicitly used in the query of PT. This prevents queries from generating infinite results like tuples with arbitrary values. So why safety matters here? Because unsafe queries may return infinitely many tuples. Like for example, we write down like t inside the way that t in r, right? These many tuples, it will return all tuples not in r, which is infinite. So databases require finite answers. So unsafe queries are not allowed. So formal query condition, we write PT is safe if all attributes of T are bound. It means every variable in T must appear in positive predicate. Like for example, you can say T in R, or you can say TA is equal to 5. Or no free variables like TA with no constraints. Then also, we should care that no unrestricted negation is there, right? So this negation is very dangerous, as I show you here. This one is dangerous. We should take care of this one. This negation must be applied only to sub-expressions that are themselves domain restricted. So all variables in T must be bounded. We should avoid unrestricted or true false. It means these can unbind variable leading to infinite results, and negation must be guarded. So example here, consider the query to find all students who have taken courses offered in biology department. So we can say for tuples in such a way that there exists R in student TID is equal to RID, and for all U in course, U department name is equal to biology, implies that there exists S in text TID is equal to SID and S course ID is equal to U course ID. Without the existential quantification on a student, the query would be unsafe if the biology department has no offered any course. So then we go for Domain Relational Calculus. This is a non-procedural query language equivalent in power to the Tuple Relational Calculus. Each query is an expression of the x1, x2 up to xn, even these predicates, right? So these x1, x2 up to xn represent domain variables, and this P is a formula similar to that of the predicate values, right? For example, you can say there exists P1x, and for all x, P1x. So for example, I want to find out ID, name, department name, and salary for instructor whose salary is greater than 80,000. Very easy. I write ID, name, department, and S. Then I say ID, name, department, and S in instructor, and is greater than 80,000, right? So this is simply ID of instructor, name, department, and salary. Then I check they should be instructor and salary should be greater than 80,000. So if you want only to get ID as the output, you write just here ID. So we write I, then we can say here I name the S in instructor and S greater than 80,000. Find the name of all instructor whose department is in Watson building. So name, we want only name. So that's why we write only n. In such a way that there exists IDs, and here I say IND and S celery in instructor table, and there exist B and A. B and A, building and budget, right? So we use A for budget. Then department building and budget in department, and building is equal to Watson, right? In this way, we write it. Next, find the set of all courses taught in 2009 fall semester or spring or both, right? We did it on other cases. So just we want courses. That's why we write here course. Then there exists A, S, Y, B, R, T. These are in section. So if we go to our tables, section table, you can see C, S, S, Y, B, R. So these are these attributes. Then we write, so what we want, C, A, S, Y, B, R, T in section, and S is equal to fall, and year is equal to 2009, then union, or because we have or here, or again same A, S, Y, B, R, T, and C, A, S, Y, B, R, T in section, this time, and S is equal to spring, and year is equal to 2010, right? This is how we can write it. If I want to write in another form, shorter version, I can write this way. I can say C, there exists A, S, Y, B, R, T, then C, A, S, Y, B, R, T in section, and in here conditions will be together. S is equal to fall, and Y is equal to 2009. Then union, S is equal to spring, and Y is equal to 2010. So the expression is safe if all the following conditions have been satisfied. All values that appears in tuples of expression are values from the domain P. That is, the values appear either in P or in tuple of a relation mentioned in P. Then for every there exists a formula, there exists x p1x, the subformula is true if and only if there is a value of x in domain p1 such that p1x is true. And for all subformula, for all x p1x, the subformula is true if and only if p1x is true for all values x from domain p1. Here, find all students who have taken all courses offered in biology department. So we want to have their ID only, right? We write I, there exists N, D, and TC, name, department name, and total credits. Then INDTC is in student, and this one should not include. And then for all course ID, TI, DN, and CR. These are in courses, right? So if we go back to our diagram, so in courses here we have course ID, title, department name, and credit. CR in course, and DN is equal to department name is equal to biology. This implies that there exists SI, SE, Y, and G, then I, SI, SE, Y, and G in text, right? So this query finds all students who have taken every course offered in biology department. This is a kind of nested quantifiers to check all biology courses. And this implication here is used to enforce that every biology course the student must have a matching enrollment in takes. So here we have I, this is the output only student ID. Then we have a student relation verifies valid students. Then we have course relation. This we check whether that the courses are in the department of biology. And in here in text, we confirmed enrollment for each biology course. Without this existential quantification on a student, this query will be unsafe if biology department has not offered any course. Find the instructors in physics with a salary greater than 90,000 with relational algebra. So we go for instructor table, then we do selection, right? We want to find instructors, so we go for instructor selection only. It means we want to have all their data, but we have a condition. It means physics department and 90,000, right? So we write department name is equal to physics, and this is and salary is greater than 90,000, right? Find all department whose name is the same as their building name. So we go for department table, we select if two condition. It means in the department table, if the values in department name is equal to the values in building column, it means okay, right? So we write department name is equal to building. Very easy, right? Then find the name of all instructors in physics, right? So the same, we do instructor, then here selection, and we say department name is equal to physics. But this time I want to have only names, right? I want to have only names, so I use pi and I say name. Find the name of all instructors in physics department together with course ID of all courses they taught, right? So in here, I need to go for two tables, right? I need to go for instructor table and also teach table. So in this way, I must do Cartesian product. Then I will apply selection and I will say department name is equal to physics. Find the largest salary in the university. So for this one, I can just reduce the tables and compare with less than, right? So it means first I will check every salary with the next salary, and if it is less than that one, I will take it out. So for this one, I need to do a Cartesian product of instructor by itself because I want to compare it by itself. So I should say instructor, and also I will do Cartesian product by itself. So I will rename it as D. So the instructor table, I make a copy and name it as D. Then selection of instructor, the main table, is less than the salary. It means the salary will be compared with the another salary in the same table, but this time with the rename, with the D name, right? Then out of here, I will take out only what I want to have, only instructor salary. Instructor dot salary. Because here I have two tables, right? D tables and instructor. That's why I write instructor dot salary. So now I want to take out from the main table to get the highest one, right? So in here I say pi salary from instructor, this one minus this. Find the name of all instructors together with the course ID of all courses they taught. In here we go for natural join. So we do instructor natural join with teach, and we will take out pi name and course ID. So we learned from the previous lecture that natural join, this natural join is similar to instructor Cartesian by teach, right? Then we will select the similar attributes, right? What are the similar attributes? So in this table, we have ID, right? And ID here. So teach.id, instructor.id. Teach instructor.id, instructor.id, and teach.id, right? Then out of here, we will take out one of them, right? Only one. I will take out one of IDs, course ID, section ID, semester, year, name, department name, and salary. Then we can say union. Then out of all, I will take out name and course ID. In this way, all instructors will be printed together with their course ID of all courses they taught. So next one, find all students who have taken all courses in CSE department. It's like the biology department, right? Same. T tuples there exist R in student where TID is equal to RID, right? And for all you in course where U department name is equal to CSE, that implies there exists S in takes where TID is equal to SID and S course ID is equal to U course ID. This T, the query returns a set of ID. So it means we want to have IDs, right? See, this TID, these represent student ID of qualifying students based on this CSE that we have here. Then we say there exists a student, TID is equal to RID. This ensures that TID corresponds to a valid student in the student table. Then we have for all you in course table, this query checks a condition for every CSE course. Then this implication, it means if U is CSE, then what happens? So this condition after this implication must hold for every CSE course. Then we say there exists S in takes where TID is equal to SID and S course ID, U course ID. This verifies that the student TID has taken the CSE course of U. So we can say there exists an enrollment record S where the student took the course U. And the last one, find all students who have taken all courses offered in CSE department, right? So we write in this way, I want to get IDs only, there exists, this is for domain relational calculus, N, D, and total credit. Then we can say I in department total credit in student and for all CITI based on the course table, right? DN and CITI department name and CR in course based on course table, and department name is equal to CSE, that implies there exists SI, SE, Y, and G. Then we can say ICI, SI, SE, Y, G from takes. In this way, we can get out all students who have taken all courses offered in CSE department. Okay, thank you very much for your attention. This was a simple introduction about formal query language. Please practice because these things will make your mindset for SQL language. If you understand these things and practice, then simply you can code them in SQL. Please practice and feel free to ask me if you have any question by leaving a comment below this video. Thank you and see you in the next lectures.